Section 4.1, Rational Functions and Asymptotes. So we're going to find domains of rational functions. We're going to find vertical and horizontal asymptotes of graphs of rational functions, and we're going to use the rational functions to model and solve real-world problems. Now, this we'll mostly do in lecture, okay? But to get the basics here, we'll go through the math language. So what we first have to do is state what a rational function is, and it's the quotient of two polynomial functions, a of x over b of x. Here, and b of x cannot be 0. Now, that's going to be an important concept for us because when this happens, this is going to tell us the vertical asymptotes, okay? So let's look at the definitions of the vertical and horizontal asymptotes. So if I look at number 1 here, it says the line x equals a is a vertical asymptote, and it has to be vertical, right, because it's at a particular x value, of the graph of f when f of x approaches positive infinity or f of x approaches negative infinity as x approaches a, either from the right or the left. So that just means that the outputs, in either case, regardless of where you're coming from, the outputs are going to go either positive infinity, negative infinity, okay? So they're just going to keep blowing up or down. There's not going to be, in what we call these are the vertical asymptotes we call pairs, okay? So you'll see that in a graph, and I'll put one up here. At the end. We'll actually graph it and show you using Desmo. All right, and the second piece here is the horizontal asymptote, and the line y equals b is a horizontal asymptote of the graph of f when f of x approaches b as x gets really big or x gets really small. Okay, so the math language will make more sense when we actually do the problem out, I'm hoping. So vertical and horizontal asymptotes of a rational function, and there's a few rules about it that we can use in our favor to make our job a lot easier. So in order to do this, what we're going to do is let f be a rational function, such that f of x is a of x over b of x, and a of x is some polynomial with degree n. So this is some degree n. And we have in the denominator some polynomial with degree m, okay? So, and then what we have to state is that a and b have no more common factors, so you cannot do any more eliminations. This is as basic as it can get. It's the smallest simplified form, okay? The graph, if we look at number 1 here, the graph of f has vertical asymptotes and zeros of b of x. Okay, so if we find all of the zeros of the denominator, we know where the vertical asymptotes would exist. Number 2, graph of the function f has one or no horizontal asymptotes determined by the comparing of the degrees of a of x and b of x. So if we compare the degrees of the numerator and the degrees of the denominator, we can make some very quick assessments of the situation of the graph. So if we look at number 1 here, number 2a, when the degree in the numerator, n, is less than the degree of the denominator, m, the graph of f has the line y equals 0, and that would be the horizontal asymptote. So when the degree in the numerator, or the top, is smaller than the degree in the bottom, then we have a horizontal asymptote at y equals 0. If we look at 2b here, when the degrees are exactly the same, then we'll have a graph of f that will have a line equaling to the degree of the lead coefficient divided by the degree of the lead coefficient in the denominator. So what these are is a sub n here is the lead coefficient of the numerator, and what b here is the lead coefficient of the denominator. And then if we look at 2c, it says when the degree of the numerator is bigger than the degree of the denominator, then we have no horizontal asymptotes. And that makes sense because the numerator will be growing much faster than the denominator. So if we look at an example here to find all the vertical and horizontal asymptotes as well as indicate the domain of f here presented. So we have f of x equals the rational function x squared plus x minus 2 all divided by 2x squared plus 5x plus 2. Alright, now let's look at an example here, and we're going to find all the vertical and horizontal asymptotes, as well as indicate the domain for the function f here, which is f of x, which is x squared plus x minus 2, all divided by 2x squared plus 5x plus 2. So the very first thing we should really look for is common factors. Okay? And in order to do that, we're obviously going to have to factor. So let's factor the numerator. And that's x squared plus x minus 2, which looks like the factors of 2 that combine to 1 are going to be x plus 2 times the quantity x minus 1. And factor the denominator. Looks like it's 2x squared, so the lead coefficient is not 1, so we'll have to do a little more work. And factor by grouping. So now what we have to do are find the factors of 4 that combine to 5. So that's easy. That's 2x squared plus 4x plus x, right? Because 4x and 1x make 5x's. And then plus 2. And then we'll factor this by splitting it in half, right? And say that this is just 2x times the quantity x plus 2. Plus, and I'm going to make the parenthesis just so I don't lose the plus 1. And then that's, now we can factor out the x plus 2, and that leaves 2x plus 1. Alright, so now that we have both of these factors here, we have the numerator and the denominator, what we're going to do is we're going to put them up here in right next to our expanded version. So we have the quantity x plus 2 in the numerator times the quantity x minus 1. And we have, oh, look at that, x plus 2 times the quantity 2x plus 1. So we do have common factors here. So now if I just copy this here and bring it down here so we can use it a little more efficiently here. That now it's clear to see that, we do know that x cannot be equal to negative 2, and we also know that x cannot be equal to negative 1/2. But what's interesting about, because we just used the zero product property, right? So we just let the denominator equal 0, right? So that would be x plus 2 times the quantity 2x plus 1 equals 0, or not equal 0 is more appropriately, and then did each one of them out. But what's interesting is that factor x plus 2 goes away. In essence, this is what we would call a hole in the graph, okay, at x is negative 2. So now all we have to do is look at this new function here, which is x minus 1, all divided by 2x plus 1. The degrees of the numerator n are equal to the degrees of the denominator m, which is 1. So we know that there's a horizontal asymptote at y equals 1/2. Now, where did the 1/2 come from? It came from these coefficients right here, the lead coefficients, right? So now we know that we have a horizontal asymptote here. Now, Now, we've already calculated out the vertical asymptote, actually. So the vertical asymptote here is given only by the denominator, which is 2x plus 1, and that cannot be equal to 0. And if you solve that out, you realize that the vertical asymptote is at negative 1/2. So the vertical asymptote exists at x equals negative 1/2. So we now have all of the horizontal and vertical asymptotes found for this particular function, f. So now we can actually put the domain together here. So the domain of f. Well, let's put using at intervals here. We know that there are specific points that we cannot be, right? X cannot be at negative 2, and x cannot be negative 1/2. So at those particular points of x, there's going to be some problem with the output, right? So the domain here is going to be, well, negative infinity all the way up to negative 2, union negative 2 all the way up to negative 1/2, union negative 1/2 all the way up to positive infinity. And that would indicate the domain. And notice what we did. We took the points of interest where they couldn't be at its lowest and its highest, and used the intervals to link it all together. If you're really good right now, I encourage you to graph f. In order to do that, you might also want to know zeros, again, which we'll talk about a little later, but we already have.